Hello guys, welcome to my YouTube channel. Today we discuss about the concept that is KKT conditions. Here KKT means Karush-Kuhn-Tucker. The definition of Karush-Kuhn-Tucker means in mathematical optimization, the Karush-Kuhn-Tucker conditions are also known as Kuhn-Tucker's conditions. This is another name of KKT conditions. These are first derivative tests for a solution in non-linear programming problem to be optimal. Here non-linear means the degree of polynomial is more than 1. These are called non-linear programming to be optimal provided that conditions satisfied. Here in KKT conditions we have to satisfy some conditions or to prove some conditions. So after that, in this KKT conditions, the first step is we have to know about the Lagrangian function. Here Lagrangian function is denoted by capital L, that is L equals to Z means objective function plus or minus lambda I into gi of x for one constant. This is the formula for giving in the problem only for one constant. If they are giving more than one constant, the Lagrangian function formula is capital L equals to z plus or minus lambda 1 g1 of x plus or minus lambda 2 g2 of x for two constant. Here after that we have to change the constant from here in the given question in KKT. Here given inequalities constant. In this KKT conditions we have to change the inequality into equality types. That means if given constants are less than or equals to type, we have to use plus s1 to changes from inequality to equalities. If given constants are greater than type, we have to use minus s1 to changes from inequality constant to equality constant. After this we have to prove some necessary condition, that is the second step in KKT conditions. Here necessary conditions to be proved. In the definition given that provided that conditions satisfy. These are all the conditions which are to be satisfied in the KKT definition. The condition to be prove or satisfy are dou L by dou x1 equals to 0, first one, dou L by dou x2 equals to 0, second one, and we have to prove that the lambda I g of x equals to 0 depend upon the constant. If given constant is 1, we have to prove this one only. If given two constant, we have, depending on that constant we prove that conditions, that must conditions. The fourth one is lambda I greater than or equals to 0 or lambda I less than or equals to 0 depend upon the question. If the given conditions are greater than or equals to type, we satisfy this condition, or less than or equals to type, we satisfy this condition. And fifth one is g of x less than or equals to 0 or g of x greater than or equals to 0. This also depend upon the question. If in the question given less than or equals to type constants, we satisfy this. If given greater than or equals to 0, we satisfy this. Here some of the rules to solve the problem are: the first rule is we have to find the Hessian matrix lambda h. We know that in the previous videos we know about how to find Hessian matrix lambda h and its principal minors. So we know how to find Hessian matrix and principal minors. The second one is we have two cases how to tell it is a maximum type question, KKT conditions, problem in maximum type or minimum type. By depending upon these two cases we can find out. The first case is if principal minors, that is lambda 1 lambda h1 mod h1 mod h2 and so on mod h1 are greater than or equals to 0. That means these principal minors ought to be positive, that is greater than 0. Okay, this is the one, and at least one from this above, any one of the one is has to be equals to 0, any one of the principal minor. Here this means, this condition means what? All this mod h1 h2 are greater than 0, else, and also at least one, that is lambda mod lambda 1 equals to 0 has to be this. Then this function is called minimum type and convex. Again I will repeat that if principal minors, that is h1 h2 and so on hn, are greater than 0 and at least one is equals to 0, that is any one of this one have to be equals to 0. The second case is if first principal minor, that is mod h1 less than 0, that is negative, and remaining minors, that is lambda mod h2 mod h3 and so on mod h1 are alternative sign, then the function is maximum type and concave. Once I am repeating once again that here principal minors, that is one principal minor, that is mod lambda h1 is less than 0, that is to be negative, and remaining coming minors are to be alternates, or that is plus or minus or plus. This has to be alternate sign, that the function is called maximum type or and concave. So here we have to note that one point, that is if f of x or g of x function is linear type, then it is directly said to be convex or minimum type. Here we does not to be do the Hessian matrix and principal minors. Here the given the directly pointed, if there is in the question is linear type condition or constant or function, here we can directly say that it is convex or minimum type. It is the shortest one to prove that it is convex or concave or maximum type or minimum type. We does not how to do the Hessian matrix or principal minors. By seeing this note, we can directly set it is a linear type equation or function, so it is directly set as convex or minimum type. Let us do an example problem. Here question given that maximize f of x or z, two or same only, equals to 3.6x1 minus 0.4x1 square plus 1.6x2 minus 0.2x2 square, subjected to 2x1 plus x2 less than or equals to 10, where x1 comma x2 greater than or equals to 0. Let us start the problem. We are given z is objective function is z equals to 3.6x1 minus 0.4x1 square plus 1.6x2 minus 0.2x2 square, and the constraint is 2x1 plus x2 less than or equals to 0. First of all, we have to change the inequality constant into equality type. Is it inequality? Here we know that if in the constant is less than or equals to type, we have to use what? Plus s1 to change inequality constant to equality constant. So here is less than or equals to type, so it is changes at 2x1 plus x2 plus s1 equals to 10 is equation 1, taken as equation 1. Okay, now Lagrange function is Lagrangian function. We have to write Lagrangian function, capital L equals to z plus or minus, we take either plus or minus here, this is nothing, equals to lambda I g of I into x. Now L equals to z means this objective function, we substitute this objective function here, 3.6x1 minus 0.4x1 square plus 1.6x2 minus 0.2x2 square, and here I am taking minus lambda 1 of g of x means this constant na, so here writing 2x1 plus x2 plus s1 equals to 10. This is taken as equation 2. Equation 2. Now we have to prove that now we have to find out, first one, take the rules. We have to find out the rules, that is, first one is Hessian matrix. We have to find the Hessian matrix for objective function, that is z equals to 3.6x1 minus 0.4x1 square plus 1.6x2 minus 0.2x2 square. Here Hessian matrix equals to what? We know that dou square f by dou x square, dou square f by dou x, dou y, dou square f by dou y dou x, dou square f by dou y square. So first we have to do dou f by dou x, which means this function to be differentiated with x. So we get dou x1, 3.6 x1 minus 0.8 x1, 3.6 minus 0.1 x1. These two came 0 0 plus 0 minus 0. This is the dou f by dou x1. Next we have to do dou square f by dou x1 square, that is again differentiate this with x1, that is minus 0.8. Okay, this came minus 0.5. Now we have to do dou f by dou x2, that is we have to differentiate this function with x2. So we came here, this is how x1, so here 0 minus 0 plus 1.6 minus 0.4 x2. Now we have to do dou square f by dou x square, dou x2 square, that means we have to differentiate this with x2, that is here came 0, this is nothing, constant 0 minus x2 cancel, we get 0.4 minus 0.4. Now here dou square f by dou square f by dou x2, dou x1 dou x2 means here is x1. If we differentiate this x2, we get dou f by dou x dou y dou x1 dou x2 equals to 0 value, because here x1 is we are differentiating with x2, not possible, we get 0 value. Same like as dou square f by dou x2 dou x1 means here is x2, we are differentiating with x1, here also get 0. So we will substitute here that dou square f by dou x square, we get value is x1 square, x1 x2, x2 x1, x2 square, we get value is minus 0.8. Dou square f dou x1, it is 0, it is also 0, in this place we get 0.4. Now it is 2 by 2 matrix na, it is 2 by 2 matrix. So we get principal minors are mod h1 and mod h2. Here mod h1 means the first element, that is minus 0.8, this is less than 0, and mod h2 means AD minus BC, A B C D, AD minus BC, that is minus into minus plus 0. Into 0.4 means 0.32 minus 0, it means 0.32 is greater than 0. Here you can see mod h1 is less than 0 and remaining mod h2 is greater than 0, it means it is alternate side. It is satisfied which condition? You can see here, if first principal minor is mod h1 is less than 0, that is negative, and remaining minors mod h2 or mod h3 are all alternate side, then the function is what? Maximum type and concord. So hence here f of x function is minimum, is maximum and concave. Now we have to do second one is what g of x. G of x, what we have, 2x1 plus x2 equals to 10 na. It is what in the note we write that here, if f of x or g of x function is linear type, then it is directly said as convex and minimum type. So here the degree of this g of x function is what we have. You can see here also 1, here also 1. Here whole degree of this equation is 1, which is linear type. So we can say that g of x is minimum type and convex. So after that we have to rules are here. We completed the rules. Now we have to satisfy the necessary condition to this problem. Let us do that necessary conditions. First one is dou L by dou x1 equals to 0. Second one is dou L by dou x2 equals to 0. We have to prove that this or satisfy this. Third one is lambda 1 of 2x1 plus x2 equals to 10 minus 10 equals to 0. We have to prove this one also. And fourth one is lambda 1 less than or equals to 0. And fifth one is 2x1 plus x2 less than or equals to 10. These 5 we have to be satisfied. Here the given constant is constant is 1 na. So we have two cases, that is case 1 is lambda 1 equals to 0, and second one is lambda 1 not equals to 0. Here take this lambda 1 of 2x1 plus x2 minus 10 equals to 0 we get that it will be 2x1 plus x2 minus 10 equals to 0. Placing here 0 lambda 1, we get 2x1 plus x2 equals to 10. Okay na? When we take lambda 1 equals to 0, we get 2x1 plus x2 equals to 10. Now we have to satisfy this all condition, that is take first one, dou L by dou x1 equals to 0 na. We have to do dou L by dou x1 means we have to differentiate this Lagrange function with x1, that is we get what, 3.6 minus 0.8 x1 minus 2 lambda 1 equals to 0. Now second one is dou L by dou x2 equals to 0. That means we have to differentiate this Lagrange function with x2. We get what, 1.6 minus 0.4 x2 minus lambda 1 equals to 0. Take this is equation 1 and this is equation 2. By substituting these two equations in the Casio, we get x1 equals to 4.5 and x2 equals to 4. This x1 x2 substitute in this equation, that is 2x1 plus x2 equals to 10. Take third condition, 2x1 less than or equal to 10. Substitute this x1 x2 value in this 2 of 4.5 plus 4 less than or equals to 10. Here 2 5 are 10, means here 9 plus 4 less than or equals to 10, 13. Here lambda in the fourth condition, here 9 plus 4 13 less than or equals to 10, it is not satisfied. Let us take the fourth condition, either lambda 1 less than or equals to 10. Here we don't know the lambda 1 value. Take this x1 value and substitute in the equation. In this equation we get 3.6 minus 0.8 of 4.5 minus 2 lambda 1 equals to 0. 3.6 minus 2 lambda 1 equals to 0. This cancel. Minus 2 lambda 1 equals to 0. Lambda 1 equals to 0 we get. Substitute this lambda 1 here. Fourth condition, 0 less than or equals to 10. Here 0 is less than 10 now, so it is satisfy the condition. This satisfy the given condition. Fourth one is satisfied. Now fifth condition we already not satisfy. This condition only fifth condition. Take the third condition here. Here lambda 1 of 2x1 plus x2 minus 10 equals to 0. Here lambda value is 0, and this 2 of 4.5 plus 4 minus 10 equals to 0. 0 into anything is 0 equals to 0. This also satisfies. Third condition. Take the first condition. Dou L by dou x1 means what? We know the value is 3.6 minus 0.8. x1 means 4.5 minus 2 of lambda 1 value is 0 equals to 0. 3.6 minus 0.8 into 4 means 6.6 minus 0 equals to 0. Here 0 equals to 0. This also satisfy. And second condition, that is 1.6 minus 0.4 of 4 minus 0 equals to 0. This also satisfies. 0 equals to 0. Here in this all conditions, first condition, second and third, fourth all satisfy, but the fifth condition are not satisfied. So the lambda equals to 0 is not the correct case for this question. Let us go for the second case, that is case 2. Case 2 is lambda 1 not equals to 0. Lambda 1 not equals to 0 means lambda not equals to 0, that is 2x1. Here if we take lambda 1 not equals to 0, 2x1 plus 2x2 equals to 10 we get. Here dou L by dou x1 equals to 0, we know that this is the value. Here we know that the x1 value, we didn't know that the lambda 1 value. Let us from this equation we find out the x1, that is 3.6 minus 0.8 x1 minus 2 lambda 1 equals to 0. 3.6 minus 2 lambda 1 equals to, this is going to right side, we get 0.8 x1. x1 equals to 3.6 minus 2 lambda 1, this is going here into, when shifting left side it is divided by, like this we can same like this only we do for the dou L by dou x2 also. We get x2 equals to 1.6 minus lambda 1 by 0.4. This x1 x2 values are substituting here for getting the lambda 1 value. Here by substituting x1 x2 value in this equation we get like this some calculations. Lastly we get lambda 1 equals to 0.4. We get the lambda 1 value. We know that didn't know that the x1 value x2 value. So in lambda 1 place we substitute the lambda 1 value. We get x1 equals to 3.5 and x2 equals to 3. By substituting lambda value in this two x1 x2 equations we get x1 x2 values. Now we have to do that satisfying the condition. The condition 1 is dou L by dou x1 is equals to 0. Here dou L by dou x1 is 3.6 minus 0.8. x1 value is what? 3.5 minus 2 of lambda value is what? 0.4 equals to 0. By doing this calculation in the cache we get this overall value is 0 equals to 0. The first, this is equals to 0, so the first condition is satisfied here. The second one is dou L by dou x2 equals to 0. Here dou L by dou x2 what we have? 1.6 minus 0.4. Here x2 value is what? In this x2 place we substitute, in this x2 place we substitute x2 value, that is 3 minus lambda value is 0.4 equals to 0. By substituting this we get this also equals to 0, so 0 equals to 0, we satisfy the second condition also. Let us go for the third condition. What is the third condition? Lambda 1 of 2x1 plus x2 minus 10 equals to 0. In the lambda 1 place we substitute the value, that is 0.4, and 2 of 3.5 plus 3 minus 10 equals to 0. That is, if we calculate this in the cache we get 0 equals to 0. That is, the third one condition also satisfied. The fourth condition is lambda 1 less than or equals to 0 equals to 0. That is here lambda 1 value is what? 0.4 less than or equals to 0. You can see here the 0.5 value is less than 0 na, so the fourth condition also satisfied. Here going for the fifth condition. The fifth condition is 2x1 plus x2 less than or equals to 10. Here 2 of x1 value is 3.5, x2 value is 3 less than or equals to 10. Here 7 plus 3 less than or equals to 10, 10 less than or equals to 10, so 10 equals to 10, so this also satisfy the condition. So these are all conditions where we have satisfied in which values? Here value x1 comma x2 and lambda 1, that is 3.5, 3 and 0.4 is the values which is maximum relative conditions. Here in the question asked that maximize f of f z equals to this subjected to this, so we can say that the 3.53 value is the values can be maximum, the given f of x function can be maximized at 3.5 and 3 value. This 3.5 and 3 value substitute in the z function, that is in the 3.6, substitute in this z function, we get z value equals to here 3.5 and 3 values, that is values of x1 and x2 are maximized to the function z. So these two values we have to substitute in the z function, that is 3.6 of 3.5 minus 0.4 of 3.5 whole square plus 1.6. Here 3.5 comma 3 values are values of x1 and x2 are maximum to the function z. These x1 x2 values are substituted in the z function, we get z value is 3.6 of 3.5 minus 0.4 of 3.5 whole square plus 1.6 of 3 minus 0.2 of 3 square. We get the value by substituting in the cache. We get z value is 10.7. Hope you love the video, guys. Like, share, comment and subscribe and click the bell icon to be notified every update from my Smart Studies YouTube channel. Hope you guys like the video and understand the concept very well. Thank you guys. Hello guys, welcome to my YouTube channel. Hope you people like the video. Keep supporting me by subscribing the YouTube channel and like, share, comment and click the bell icon to be notified every update from my small studies YouTube channel. Thank you guys.